So, hello everyone. Let us discuss this wonderful problem on the chapter of electromagnetic induction. So, in this particular problem, the problem statement goes like this. Two coils A and B are made by a winding of a conducting wire in one layer without gap between adjacent turns into identical cores having high magnetic permeability and electrical resistivity. Okay, so this means that both the coils that you are talking about have a very high uh, magnetic permeability, meaning they have some way of increasing the inductance. We know that the inductance of any coil is given by this result if it is a long solenoid, mu naught n square, where n is turns, n square by pi r square divided by the length of the coil. Now, since both of them are tightly wound with the same wire, the turns per unit length will be the same. Turns per unit length would be the same. So this would mean that if the turns per unit length n, which is n by L ratio, is same, this means if you increase the number of turns, automatically the length also has to be higher. Okay, so this is one thing we have to be careful. Now, it is said that the number of turns have been doubled. Okay, and since the number of turns have been doubled, we can say the length of this system should also be double. You cannot increase the number of turns unless you are changing the length of the total coil on which winding has happened. Okay. So that is one trick in this particular problem. So L, which is not just proportional to n square, which has been doubled, because you have the turns per unit length a constant. If you double the value of n, the value of length also will be doubled. So this will mean the inductance will be directly proportional to n square upon L. So this has been doubled, so it becomes 4 times. This also has been doubled, so it will divide by 2. So overall, the answer will be divided or multiplied by 2. So this means the inductance of the second coil B will be twice the inductance of the first coil A. Okay, that is the first half of this problem. So next, the wire used has a very small resistance. So this means we will ignore the resistance of the coil themselves. And the self-induced voltages would be quite high. That means back EMF. The circuit is arranged by connecting parallel connection of these coils and a capacitor across the battery of EMF E and internal resistance R, so as shown in this figure. So they are saying if the circuit is opened after keeping it closed for a long time. So this means the circuit is closed for a long time. So this switch is closed. And at t equal to 0, it has been opened. They're asking us what is the maximum value of the when the charge on the capacitor is maximum. So this would become a combination of a inductance and a capacitance system, which is called a LC oscillator. In this system, the current in both the coils are asked. The maximum charge on the capacitor is also asked. Okay. So what are the concepts we will require for this problem? The first one, which we already discussed, is the way in which inductance is calculated. And we obtained inductance of B is twice of inductance of A. Then we should also know what is the steady state analysis of a capacitor and inductor. In steady state, the capacitor charge becomes a constant. So rate of change of charge will be 0. So this means it will become an open circuit. The inductor, on the other hand, will not have any change in its current or flux, because of which it will behave like a short circuit, or there will not be any opposition from the inductor. So inductor behaves like a short circuit at t equal to a long time. Okay. Now, when the switching is suddenly done, the flux in the circuit should not change. So the inductors will try to maintain their current. So both the inductors will have a downward current, and this downward current will go from the capacitor, because as the switch is open, this side current can't flow. So all the current that is coming from these two will then have to go through this capacitor. Okay. So just after the switch is opened, you'll observe that the capacitor will have some slowly accumulation of charge taking place because current is flowing into it. So at any instant, we can say the current in the inductor sum should be equal to the current in the capacitor. And when the capacitor has maximum charge, the charge is maximum. Any function is maximum, its first derivative should be 0. So this means when we want to solve for the capacitor being maximum charge, we can equate the dq by dt in the capacitor as 0. And this will mean that the capacitor's current should go to 0. And since IA plus IB should be 0, we can say that the inductors will also have no currents. And also we know one more thing, that IA and IB will be related to each other through this equation, that they are in parallel, so the voltage across them should be same. So minus LdI by dt minus, sorry, here there should be a 2 here, pardon me. So this will be 2 LdI by dt, they will cancel out each other. So this means the current will be related as IA is equal to vice of IB. Okay, so this will so IA is 2 times of IB. So this means we can say if one of them is 0, the other one will also become 0, because the sum of these two has to be 0, and also they are related through this. So we can say when the current in the capacitor is 0, or the charge in the capacitor is maximum, the current is 0, current in both inductors should also be 0. Now, they have also asked us what is the maximum charge on the capacitor. So this we'll do through the energy conservation. So initially, the capacitor, if you look at the circuit of the capacitor before the switch is opened, both the inductors are short circuit, so there is no voltage drop across them. So the capacitor has Q equal to CV, and since the voltage drop across them is 0, the capacitor charge is also 0. So all the current is in the inductors. IA plus IB will be equal to this I naught, and we know I naught will be E by R because this is short circuit. So E is equal to IR for this loop. So hence we can say the initial current will be I by R through the battery, E by R. So now the two inductors are identical in the sense that they are parallel, not identical. The inductance of them is L and 2L. So they will effectively act as two parallel combination of an inductor. So hence the effective inductance is L1, L2 by L1 plus L2. That gives you 2L by 3. So initially the energy in both the inductor combined will be half L effective into sky energy square plus the energy in the capacitor Q square by 2C plus the energy later on in the inductors. And since we are saying that the inductors have 0 current, this term goes to 0. So Q square by 2C should be equated to the initial energy. When I do that and I simplify it, I'll get my final charge as E by R root 2LC by 3. So this problem tells us few aspects. One important thing is the inductor will have 0 voltage difference if it is in steady state, and it will be behaving like a short circuit. Capacitor will behave like a open circuit. How to relate inductances when turns and turns per unit length are given. These are now other things we have seen. Okay. I hope you understood. If you have any queries, you can always comment in the comment section. We can have a further discussion. Okay. Thank you.